Hello, today we are going to talk about the definition of derivative. So before then, let's review what we talked about in last class, the secant line and the tangent line. So if you remember, if I have a curve to finding the tangent line of this point, I will find a secant line that these 2 points are close enough. The shorter distance that as the point B, let's say as point B approaching to point A, then the secant line of AB is going to approaching the tangent line of A. Okay, so remember the slope of a secant line equals to what? Well, if you have a 2 point, this is going to equals to the change in y over the change in x, right? And then the change in y is f of point A minus the f of point B over A minus B. That's the slope of a secant line. So to get the slope of a tangent line, we want the distance between A and B are as closer as possible. Let's say this is our first B, and then we found another B even closer, B prime. So A, the tangent line, the secant line A, B prime is going to become a better estimation for the tangent line of A, right? Or we can find something even closer. They could be on the other side, such as B double prime, right? This will give you a better estimation. So how do we represent that? So we can say a point 8 and the distance between point A plus H. H, suppose the distance between A and B could be positive or negative because the distance can be on both sides as long as they are small enough. So, okay, so in more general, let's talk about more general. In general, if you have a given point X and we want to estimate is tangent line slope, or the slope is slope of its tangent line. We want to find another point close enough to X. Such as a point S plus H. S can be very, very, very small. All right, so the slope of X to S plus H can be returned as the changing of Y minus the changing of X. So that's the change of Y. Okay, let me give you more detail. Our Y coordinate would be what? The S plus H minus X. That means the Y coordinate very close to the point X. And then our S coordinate would be S plus H minus X. To simplify it, we got this function. So this is also called the differences of quotient. You may see it somewhere in your pre-college algebra classes. Pre-calculus class or college algebra classes. So as long as H is small enough, the slope is going to be approaching to the tangent line. So the definition of derivative for a function y equals to fx is derivative at x is the function f of x defined by f of prime x equals to the limit as h very close to 0, that means approaching to 0, fx plus h minus fx over x. Okay, so if the limit is x, that's very important because last class we talked about limit sometimes could not exist. So if the limit is, then we can say f is differentiable at x. The process of finding the derivative is called differentiation. Okay, so this f prime of x is read as f primed of x. You might see another notation, but usually when we denote the derivative of y equals to fx, the most common one is f prime of s dy over dx. Sometimes we write it as y prime, sometimes we write it as d dx, and then f of fx, or capital D, the little s, and y. Okay, so dy over dx is read as the derivative of y with respect to x. So this is the definition of the derivative and the other notation that you might see from the other textbook or in your exercise. Okay, so here are some examples of a tangent line or the derivative of a function. So if you have a function all right, so let's find the tangent line of point A, B, C, and D. So what will be the tangent line? So the tangent line for point A should be a what? Horizontal line. Because at that point, the rate of change should equal to 0, the instantaneous rate of change. I should be more accurate about that. And then at point B, the derivative should be, the tangent line should be what? This one, right? Oops. So in this case, at point B, the derivative of fx or of y is going to be a negative number, because remember the slope of the tangent line is the derivative. Okay, so now the slope is a negative, so that means the derivative is going to be a negative number. And the c, again, this is going to be another horizontal line. So the instantaneous speed at point C is not going to change. And at point D, I'm sorry, it should be D instead of C. At point D, here should be positive because the slope at this point is going up. So when it comes to a graph like that, when we try to estimate the derivative, we can think about, hey, the derivative at point A, where A could equal to a positive, a whole integer, which is 1. They could be number as fractions, which is 1.1. Right? They can also be a negative. You can have a negative derivative, like say this is point E, the derivative at point E exists, and let's say this is negative 1.2. So we can find the derivative at x equals to negative 1.2. Well, in here, it's going to be, the slope is going to be a positive number. We can even think about the entire interval. Like, for example, in this case, from point A to point E, I'm going to highlight it in red. Oops. For this interval, the function is going up, right? Fx is going up. On interval from E to A, let's do an open interval, because when it comes to point A, this is going to be flat-lined. The function fx is increasing, but what about the derivative? All the slope are also positive in that interval, right? All the slope of the tangent line are positive. So we can say f prime of x on interval E to A is positive. Okay, and now take a look at this part. From A to C, on this part, on interval, from A to C, the function is decreasing. So all the slope in this interval is going to be negative, right? So we can say f prime of x on interval A to C is a negative. Similarly, from C to D, it's going to be, the derivative is going to be positive. So the value of f prime of x definitely depends on the value of x. And the f prime of x is a function of x, because as you can see, the instantaneous rate, the instantaneous rate is going to change as x changes, right? So that means the slope, the derivative of the x is going to change. Okay, so now let me give you an example about how to estimate the derivative. So let's say, hey, given me a function fx equals to negative 3x plus 8, I want you to find the slope of the tangent line. Well, remember by the definition, the slope of the tangent line is equals to the slope of the secant line as h approaching to 0. So the slope of secant line, how do we find it? Well, the slope of secant line is equals to the difference of a quotient, right? That is by definition. All right, so now fx equals to negative 3s plus 8. We already have that, and we still need to find f of s plus h. So f of s plus h equals to negative 3 times x plus h plus 8. Okay, you can simplify here or you can simplify it later. So if I simplify here, I have negative 3 plus h plus 8. And now we substitute these into the function. And also we need to substitute fx equals to negative 3x plus 3 in here, right? Because this part is equal to fx. So the limit of this, I should write it equals to negative 3x minus 3h plus 8, subtract the entire fx. So it's very important for you to put the parentheses, otherwise you might calculate this wrong, because when you have a subtraction, this is going to change the sign inside of the parenthesis. This is very common based on my experience on college algebra or pre-calculus classes. Okay, so as we continue to simplify it, we got cancel these two. So I have negative 3h over x, over h, sorry. By the definition, this should be divided by h. So that when we continue to simplify, I have h approaching to 0 is equal to negative 3. So that means as h goes to 0, the limit is equal to what? Negative 3, because there's no more h here. All the h is being cancelled out. That means this is a constant. So that means the tangent line is going to be a constant. Okay, is this a little bit hard to understanding why the tangent line is constant? So now let's take a graph. What does this graph look like? Well, this is a linear function. On the graph, the linear function is what? Negative 3x plus a. So the graph is going to look like this one. Right? So on any given point, so if I have a point A, in here, I want to find the tangent line of this point A. It's going to be this one, right? Which is overlap the same original function. If I give you a point B, well, take a look. The slope is going to be the same. The slope of this tangent line is going to be the same slope as the original function, which is all equal to 3. So that means the rate of change is going to be constant. That means all of the instantaneous rate of change is all equal to 3. Negative 3, I'm sorry. So that means what? Our derivative is equal to negative 3. It's correct. All right, there's some other cases, such as when you see a parabola, like the most basic one, we know that the instantaneous rate of change is going to be different, because in here, the slope is negative. At point A, the slope is going to be a negative, but at point B, the slope is going to be a positive number. So what does the derivative of this function look like? Well, let's try to find out. So I have a function y equals to x squared. All right, so I want to find the derivative of that. So I have the slope of the tangent line equals to the limit as x approaching to 0 the slope of a secant line, where the slope of a secant line defined by s plus h minus fx over h. Okay, we have fx equals to x squared, and then s plus h is equals to x plus h squared. When we simplify, I have x squared plus 2sh plus h squared. Okay, so we substitute back in here. As h approaching to 0, I have x squared plus 2xh plus h squared minus x squared over h. Simplify it. So the s squared got cancelled, right? Because we have a x squared and negative x squared. So now I have the limit h approaching to 0, 2xh plus h squared over h. They have a common factor, h. That means I can cancel them. So now I have the limit as h approaching to 0, 2s plus h. That would be the tangent line, the slope of the tangent line for this function. So as you can see, as we are not done yet because we still need to calculate the limit. So as h approaching to 0, so the limit of 2s plus h is going to equals to 2x, right? Because h equals to 0, approaching to 0. All right, so that's the slope of the tangent line. Also the f of prime of x for this function. As you can see, there's an x here. That means what? Well, that means the derivative is going to change. The slope is going to change based on with respect of to x, right? So for example, at point A, let's say point A at -2 and point B at +3. So that means the slope at -2, f prime of -2 equals to what? F prime of x equals to 2s. So that means f prime of -2 is equal to 2 times -2, which is -4. So that means the slope at this point, the instantaneous rate of change at this point equals -4. And then what about point B? B is at 3. So f prime of 3 equals to our function 2 times 3, which is 6. So that means the slope of the tangent line at point B equals to 6. Okay, so and there's a way to check it, such as look at point A. Point A is decreasing, right? The slope is going down, so it makes sense that the slope is a negative number. And then at point B, the function is increasing. Increasing means what? The slope at that point is going to be a positive number, so that means it's 6. We can also compare to another slope at here, such as at 1. So f prime of 1 equals to 2 times 1 equals to 2. So that means the slope at x equals to 1 equals to 2, whereas the slope at x equals to 3 is equal to 6. Do you see the differences here? They are all positive, but one is smaller, one is larger. Because of what? Because at point 1, the line, the tangent line is not as steep as point 3, right? As x gets bigger, the increasing rate gets faster. So that's why the number, even though they're all positive, the number could be different. So that's it for the derivative. Let me know if you have other questions.